Hey guys, it's Finn. In this video, I'm going to fix a few problems that we had, and furthermore, I'm going to fix that when we create a new node between if we replace a connection with a new node and two new connections, that this new node has always a new innovation number. Because, well, theoretically, if one genome replaces a connection and a different genome replaces the same connection, in theory, they could also have this new node in the middle should have the same innovation number. So before I do that, I'm going to fix one very important thing, and it's in the connection in the genome, and in here in the crossover method, there was a huge problem because for me there was the if clause. Then there was another if clause, so there was no else. And the effect of that was that there were nodes without connections, and this is obviously wrong. So you obviously don't want to have any nodes without connections or any connection that ends in nowhere and so on. So make sure that you have this if, else if, and else. Same for the distance. But the weird thing is that I only had it for the crossover method, but not for the distance method, and I copied this to the crossover part. So for some reason I deleted it at some point. Okay, so the problem with creating a new innovation number for a new node is, well, I fixed it this way. So in our connection gene, I am adding a replace index, and this replace index tells us if we replace this connection by a new node gene and two new connections, that the node in the middle should have this index or this innovation number. So what I did then is I went into the need class, and up here I created two new methods. So what they do is the following. Basically, we can set a replace index to a connection that is in between node 1 and node 2. So I give him two nodes, node 1 and node 2. It gets the connection in between, so all connections that get new connection gene from 1 to 2. And then on this whole thing, we call set replace index to the index. Yeah, well, I should have mentioned that in here we've got the replace index and also a set and get method. I also implemented a toString method, but you don't really need that. I just needed it for debugging, so you can just leave that out. So when you have the get and setter for the replace index, we go into the need class, and in here you can set the replace index to the connection between node 1 and node 2. I did not really check if this connection exists or not. I'm just assuming that it does. So if you put two nodes in here where there has never been a connection, this is going to return null, and, well, this wouldn't work. But in my code, I ensured that this connection always exists, so I do not have to check this. The next method is a get replace index. Basically, it looks the same, so I give him two nodes. And, well, I need to do the checking here. So the first thing is I get the connection. I create a new connection based on these nodes. And, well, I always needed this connection to use my hash set with my hash map, and I gave him a connection with node 1 and node 2, and it returned me the connection with all the important data like the innovation number and the replace index. Well, that's the new thing. So I can get the replace index by getting the all connections.get with the connection, and this is basically my data object. Well, if this connection has never existed, it's going to be null, so the replace index is going to be 0. 0 means that, well, there is no replace index, and we need to create a new node in the middle. Otherwise, we can simply call data.getReplace or return data.getReplace index. Now we need this in the genome class because down here in the mutate link method, mutate node method, I changed a few things. So what I did is most of it looks the same, but in here the first thing I do is I get the replace index. This shouldn't be there, so this is just for demonstration later on. So I get the replace index for the connections that we just choose, and, well, yeah, I get the replace index. it could either be 0 or it could be a different number. So if it's 0, this new node in the middle is going to be new created. I set the x and I set the y value, and I set the replace index because we took this connection, replaced it with this node in the middle, and this is like a new node. We set the replace index from to 2 to this new innovation number. Well, if the replace index is not equal to 0, we create a new this middle node can be we can get it from the need class by simply calling get node with the replace index. So well, this is actually it for this method, and I'll show you the effect of that. So if I set replace index to 0, it's always going to be a new node in the middle. So basically this, if I set this to 0, this is not activated. So basically this is what we had the last time, and my settings is the following. So my my mutations are rather low. My mutate node method is the highest because I wanted this to be like very high to see the effect of that. So if I go here, I've got 1,000 clients and 100 iterations. So what you can see is down here, I printed at the end every genome, and these are like this line is one genome with the connection innovation number. So it has 8 connections, and these are the innovation numbers. And you can see that these innovation numbers get really high, like 19,000, probably even higher at some point. So like this is really high. So they're like every time new connections for every new node and so on, and new node for every new call of that method. So if I go back into the genome and replace this replace index equals 0, you can see that it does use the same node in the middle if it has already been created by one connection, and we never go above 1,000, or actually we do. We go above 1,000, but we do not go that much higher. So you can see that it's the amount of new connections and new nodes that we create is so much less. And well, this is basically the idea of need, that you that this is going to be similar with same innovation numbers when it's like it should be the same. So replacing one connection on 2 different genomes results in the same result. And well, this is like pretty good, and it has a performance increase later on. So I hope you liked it, and I hope to see you in the next video.